Hello, lords and ladies. Sorry, that was weird. Let's talk about a swinging pendulum. All right, we're going to look at three instants. Instant 1, left side of the slide, we are assuming this thing is at a maximum height that we're going to call h, as measured from, as you can note in the diagram via instant 3, here's h0. So this height is h. Instant 1, we got a little bar graph here of kinetic energy and gravitational potential energy at various instants in this thing's swing as it swings. And we've got a semi-filled in bar chart here with some givens in orange. Now we are going to neglect things like air resistance slash, any frictional loss that maybe happens when something rubs against something else. Okay, so neglecting that sort of stuff, well, here's what we know. We know, but when I say we, I qualify to mean my students. My students have done a lab where we looked at these energies. We looked at different amounts of energy that a pendulum had at different instants as it swings, and we came up with the fact that mechanical energy, which is the sum of kinetic and gravitational energies, mechanical energy is constant. Mechanical energy is conserved. All right, that's going to be an answer down here. Well, mechanical energy is conserved. When someone asks you a question on an exam or something like that, on some sort of assessment, and you are trying to explain how you know, that is called stating a major principle. Well, because mechanical energy is conserved, that allows you to say, maybe go down the road to saying some more important stuff, or some more to explain some important stuff. So we happen to know here, because we're given the fact, we happen to know that at instant 1, this object, well, the Earth pendulum system has 1, 2, 3, 4, 5, 6 bars worth of gravitational potential energy. And if it's at max height, that's a way for us to say, maybe instead of saying V initial, I'm going to say V1. V1, the velocity at instant 1, is 0. All right, when this thing is as high as it's going to get, it's not moving. So therefore, this energy, kinetic energy of the bob, is 0, and mechanical energy is a total of 6 bars. Okay, later, at instant 2 here, well, mechanical energy must still be constant. If this thing tells us that there are 4 bars of gravitational potential energy, that means there must be the other 2 of this thing's kinetic energy, the bob's kinetic energy. And then at instant 3, if we say that mechanical energy is still conserved, all these mechanical energy sums have to be the same. Now, notice we have said at instant 3, we have defined that height to be 0, and that means this system has, the Bob Earth system has 0 gravitational potential energy. But if mechanical energy is conserved, there must still be 6 total bars. That's how much kinetic energy there is. Yeah? So what we are explain my answers, we can literally say like, well, K1 plus UG1 is K2 plus UG2, right? And then if we say, well, this was 0, and this is, quote, 6, and this is, quote, 4, and this must be, quote, 2, and we're not using units here, but we're using concepts. Okay, here's a neat question. Then draw an accurate position for the pendulum at instant 2 based on the graphs. Well, here's something that we can say for sure. All right, notice, here's one thing you can do. You can compare gravitational potential energy from one instant to a next, and you can do it, somewhat quantitatively. Right? We know that UG2 is 4/6 of UG1, right? We get that? UG1 was 6 and UG2 is 4. So UG2 is 2/3 of UG1. Well, that must mean, because UG is mgh, well, the mass is the mass, and Earth's gravitational field is what it is. That must mean that height 2 is 2/3 of height 1. Because UG is proportional to height. So if there's 2/3 as much gravitational potential energy, and I'm saying, look, because this was 6 and that's 4, that's 2/3 as much, the height must be 2/3 as high, so watch what we can do. We can pretty accurately, with our use of spatial goodness, break this height into 3 parts, and here's 1/3, 2/3. So it looks like our pendulum is about this high up, right? Notice here's my 2/3 h, 2/3 h, as compared to h. So there's where the object is. Want me to draw a string? I'll do it. Yeah? Okay? Not bad? So one, we for sure need to be able to apply conservation of mechanical energy. 2, sometimes we can relate one energy to another at different instants if we know something about, well, sometimes we can not only relate the energies, but that means sometimes we can relate other things, like in this case, the heights. Okay, let's look at another. Scratch that. Also scratch that. There we are. Now, this doesn't only hold mechanical conservation of mechanical energy does not only apply to pendulum. So mechanical energy is conserved under the following criteria. 1, we neglect, quote, non-conservative interactions. Oh boy. It says non-conservative interactions. Interactions is a way of saying forces. And so we're neglecting things like friction and air resistance and people just pushing things. And so the big deal, this is sort of the same thing as saying, I'll make this a star, only conservative forces act. And conservative forces, well, one of them is gravity. Gravity is a conservative force. So while this thing is in the air, after it's shot, while it's in the air, you know, this is the VI is the instant just after this thing has left whatever launcher fired it. All right, from that instant on, as this thing moves, it is acted on by nothing but gravity. That's a fact. All right, there's no force that keeps things going. So as this thing moves through space, the only thing that makes it change at all, its motion at all, is gravity. All right, and so this is a conservation of momentum, conservation of mechanical energy scenario. All right, so here are 3 instants. We've got instant 1, we've got instant 2, we've got instant 3. Notice, right, here's instant 3. We're calling this down here height 0. Here's instant 2 at the very top. I'll say peak. Here's instant 1. Okay, we have defined a couple of things somewhat arbitrarily here. There's no way in the world to say, wait a minute, shouldn't it have more U than K? There's no way to do that without numbers, right? There's no way to compare those two to each other. But let's see, what can we do? Well, we can for sure say this, right? I know that if height 3 is 0, then that means UG3 is 0. And I know if mechanical energy is conserved, right, this plus this equals this plus this equals this plus this. So that means there was a mechanical energy of, quote, 6. Okay, 1, 2, 3, 4, 1, 2. So there's still a mechanical energy of 6. 1, 2, 3, 4, 5, 6. Here's your bar for instant 3. Right? Again, gravitational potential energy of the Earth mass system is 0 because this thing is... all right, this is interesting. I hear you saying, but the thing hit the ground, so it stopped. There's no K if it stops. But, right, check this out. We're saying that gravity is the only force that acts. When it hits the ground, well, there's a huge non-conservative force of the ground pushing on the object. So this instant 3 is just before it lands. Just before landing. That's one you have to be able to accept. All right, we'll say it's at the ground even though it's not at the ground. All right, it's infinitely small distance above the ground, just before landing. Okay, K is not 0. The thing has not stopped. It's actually moving as fast as it will move. All right, so then how do we do instant 2? How do we say how much is there? Well, here's where, you know, some interpretation of the diagram can help. Watch this. Here's a height here. Here's a height where this thing started. Here's a height at the bottom. So, you know, we could pretty reasonably say those are about the same. I mean, maybe my line here is a little bit squirrely, right? Maybe that I could have made that a little more horizontal. Right? Maybe this line is... I'm trying to cheat a little bit now to tell you the truth, but I'm trying to say, oh yeah, that's great, right? So this is like height max. This is like half of that height, right? You dig? So what that means is if there were 2 units of gravitational potential energy at instant 1 at height h over 2, when the object goes twice as high up, because UG is mgh, we must have twice as much gravitational potential energy associated with this system. So we go from 2 bars up to 4. And that says if mechanical energy still has to be 6, well, K must be 2. And the story we're trying to tell here is not that, well, yeah, this, you know, these always just switch. We're not trying to say this turns into that and that turns into that. That's not the case. The sum always has to be the same. It so happens that height changed by a factor of 2, and thus gravitational potential energy changed by a factor of 2. All right? Because this was at height h over 2. This is at height h. Okay? And this checks out because what's this thing do as it goes from instant 1 to instant 2? Well, this says the thing slows down. There's less kinetic energy. And sure, as something goes up in the air, this thing goes from here to here, it slows down. And notice this is pretty too. It's not stopped. Kinetic energy is not 0. This is max height, but kinetic energy is not 0 because this thing is at the top of its trajectory, good vocabulary word. This thing is moving that way. I'll call that V top. I should call it V2. Why don't I call it that? You could do that too. All right, so this thing is moving just slower than it was before. Okay, down here, it's moving faster than it did before. There's V3. I'm drawing those velocities tangent to the curve. That's not the worst thing in the world for you to notice. For my folks, it's not something we've talked about just yet, but it's pretty good to be able to feel comfortable with. Okay? But the major thing that we're trying to accomplish here is we're trying to employ, come to grips with that, right? As long as we're neglecting any interactions between system and non-conservative stuff, right? if gravity is the only force that's acting on an object, or that if gravitational interactions are the only interactions that happen in a system, gravity is defined to be a conservative force, that means mechanical energy is conserved. Mechanical energy at any one instant and any other instant must be the same exact amount. All right, and we can conceptually look at that by quite literally doing these bar chart things and given a consistent number of bars. Okay, we looked and spoke about this instant. Something real interesting about this is we'll say, you know, some questions will say when it hits the ground. What they mean is not when it's on the ground, but infinitely small amount of time before it hits the ground. Just before. So even though we say height 0, you can't think, well, it stopped. Notice, lots and lots of speed. The most speed. Because just before hitting, this thing is moving really fast. It has to, because the system, as we've defined it, with height 0 being here, has no gravitational potential energy. All the system's energy must be this kinetic energy. Okay? Okay, folks. See you soon.